All right, so I'll be going through this work example problem. It comes from ACE Physics Syllabus Code 9702, paper 21 from May, June 2016. State what is meant by elastic potential energy. And a moment ago, we were talking about this, and I said, energy stored in an object due to a change in its shape. Change the shape of a spring by stretching it out. It's got energy stored in that spring, elastic potential energy. And again, the work that you do in stretching the spring out, work is force times distance. The work you do in stretching the spring out is equal to the elastic potential energy that it possesses. Part B says a spring is extended by applying a force. The variation with extension x of the force F is shown in figure 4.1 with a range of values of x from 20 to 40 centimeters. Okay. It says use data from figure 4.1 to show that the spring obeys Hooke's law for this range of extensions. We say that a spring obeys Hooke's law when the force applied is proportional to the extension. So by inspection, we can look at this and go, yep, that's a line that obeys Hooke's law. Like if this is a straight line, then the force is proportional to the extension, right? So for a given, increase here, we get a proportional increase in the force, or for a given change in the force, we get a proportional extension. That's because this is a straight line. How else might we be able to sort of show that? You could look at some data points. If I zoom in right here at the 30 centimeter mark, extension, I can read off that it crosses here. And so this is 7.5, 7.6, 7.7, 7.8. So you've got this coordinate 30 centimeters corresponding to 7.8 newtons of force. Okay, if we think about what Hooke's law is, it's saying that the force is equal to some spring constant times the extension. And there's a negative sign in front because if we stretch a spring out, then the force in the spring is like pulling back the other way. So like the force vector, the force in the spring always opposes the direction you've either compressed it or extended it. So there's a negative sign that indicates the opposition of these vectors. If we think about what the constant is here, we're trying to show that the spring obeys Hooke's law. We should get the same constant, the same proportionality for force to extension. So I can calculate K here, taking the force divided by the extension, and I'm going to put it in meters just because we're used to seeing K, newtons per meter for your lab work this week. That's the way I want it reported, newtons per meter. So here it looks like there's a spring constant, 7.8 divided by 0.3 of 26. K equals 26 newtons per meter. Now I could test another point, and if I get the same constant, then it's showing, yeah, this is obeying Hooke's law. Again, I kind of already know because, yeah, it's a line, right? Like it increases, it's linear. This point right here at 25 neatly crosses at 5. I'm sorry, 6.5. So here I've got a data point that is 25 centimeters over on the x-axis. Put a comma there. 25 centimeters and 6.5 newtons of force. So if I take K equal to force divided by extension, 6.5 newtons divided by 25.25 meters, rather. 6.5 divided by 0.25. I sure enough get the same spring constant, indicating that it's a constant, right? So it's obeying Hooke's law. So you'd want to kind of, it does say use data from the figure. And so sometimes it'll say without calculation, explain something. It's just kind of wanting you to sort of qualitatively sort of, interpret the data there. But here it says, use data. And so we could actually test it and say, because force is proportional to extension, the spring obeys Hooke's law. And you can say like, oh, for this range of extension. And the calculation here sort of shows it out. You could go, to ensure the marks if you wanted to, you could go on to say, for a force of 7.8 newtons, the extension is 0.3, giving a spring constant of 26 newtons per meter. By examining another point at 6.5 newtons of force, the extension is 25 centimeters, resulting in the same spring constant, 26 newtons per meter. So you could kind of like spell out what you did with your calculation here in order to further prove your mastery of that learning objective, which is really about sort of Hooke's law. The question goes on to ask us to calculate using the figure the spring constant. Well, that's what we're doing for our lab work this week. This will be good practice for us. How do we calculate the spring constant? Well, we already did it. Okay, it's the slope of this line. So what I did was I took a single data point and I calculated K using that data point. All right. Then I chose another data point and I calculated K again, and I got the same value. But could I use these data points to actually find the slope of this line? So the rise will be the change in force, the run will be the change in extension, and rise over run is the spring constant, newtons per meter. Also be a newtons per centimeter or newtons per meter. They wanted a newtons per meter. All right, so I'm just going to use the same data points that I got a moment ago. And so the difference in the y values is going to be 7.8 minus 6.5. And at 7.8, there was a 0.3 meter extension. And at 6.5 newtons, it was 0.25 meter extension. These are newtons, of course. 7.8 minus 6.5 gives me 1.3 newtons for the rise. And then 0.05 meters. So 1.3 divided by 0.05 is still 26. It now asks us to use that figure to calculate the work done extending the spring from 20 to 40 centimeters. And so how much work is done to extend the spring from 20 to 40 centimeters? Work is force times displacement. The displacement here is given in centimeters, okay? What we have to do is calculate the area underneath this curve. The area underneath this curve will give us the elastic potential energy stored. So it looks like I've got a triangle and a rectangle if I kind of break it down like this here. And so that's an important note to maybe have in your journal there, that the area underneath a force extension graph gives the elastic potential energy stored in the spring. I'm sorry. Maybe I jumped ahead. They want us to just calculate the work done. Earlier I said like the work done is the elastic potential energy. We define this first. Like we're calculating both the work done, right? It's the force times the extension is equal to the energy stored in the spring. It's the area sort of underneath this curve. So this is 5. Then I have here 5.2, and then it goes all the way up at 40 centimeters. 10.4. So if I calculate the area of this triangle, it's going to be 1/2 the base. The base is 20 centimeters. 1/2 base times height. 1/2 20 centimeters, 0.2 meters. Okay. Now the height is the difference between 10.4 and 5.2. That is 5.2, right? 5.2 newtons there, and so I have Newton meters. Don't forget, we have this tiny little rectangular part of the curve that we need to calculate too, because it's still under the curve there. And so it has a height of, the difference between 5 and 5.2. So it's a height of 0.2 and a width of, 0.2 still. So it's got our 0.2 meter base, so just like base times height. 0.2 times 0.2 newtons. So here we've got 1/2 times the base times height. So 0.52 joules for the triangular part of the graph, 0.2 times 0.2, 0.04 joules for that little rectangle down there. Add them together, and we get 0.56 joules of work done to stretch that spring out. It says a force is applied to the spring in B to give an extension of 50 centimeters. State how you would check that the spring has not exceeded its elastic limit. Does anybody know how you would check to see if the spring has exceeded or not its elastic limit? Yeah.
If you alter the force, doesn't A equal to
You're saying we could calculate what this force is, right? But then we'd have to be able to compare it to like a list of like, do not exceed this force, right, for the spring. And we'd have to be given some information about the spring in order to sort of do that. So you're right, we know enough about the spring. We know it's constant. We know what the extension is. We could calculate what that force is numerically, quantify the force, but then we don't, how do we know whether or not it's exceeded its elastic limit based on that? Unless we were to publish something like, do not exceed a force of blank for this spring, otherwise you'll plastically deform it. So how would you in the laboratory go about seeing that? Okay, we actually encountered this during our lab work this morning. So if you want to watch, that data collection is posted. And I think after like the third data point, I said, how could we check and see, have I already plastically deformed the spring? Take a look what's written in tasteful pink chalk there on the chalkboard. It says elastic deformation is when the object returns to its original shape when the force is removed. And that's really the key to answering this question, right? So how can we check that it has not exceeded its elastic limit? Remove the force, whatever it is, we could calculate what it is for this extension, that spring constant. Remove the force and see if the object returns to its original shape. If it does, we have not exceeded the elastic limit. So be careful to always answer the question, like state how you would check. If I just left my answer at remove the force and see if the object returns to its original shape, I haven't really done enough to answer it. You have to then say like, well, what does that tell us if it does or doesn't? Like, if it does, then we have not exceeded the elastic limit, right? Because by exceeding the elastic limit, it will never return to its original shape. That's a permanent deformation.